Well, our test 2, we've got, the chapter 16 Think Well material on techniques of integration, all those fun ways to get all those formulas from our table. And chapter 16 in the Think Well, or the chapter 8 worksheets, 8.1 through 8.5, but not necessarily in that order. But what we're going to be looking at, as some of you have already asked, how many problems are going to be on? There are 10 problems. So, yes, I do want you to be able to finish tomorrow. So, but that means each problem is worth twice as much as usual. Well, usual for you, there's not really a usual. But I'll still count 5 points each, but that'd be out of 50 points total. So, in the 8.1, we introduced the table table of formulas, something like that. And you've probably been using those at least a little bit on, I don't mind if inside a trig substitution, if you run into like the integral of cosecant theta or an integral of secant theta, just go to the table, use that. There are some of the problems I will say do not use the table, well, for the main portion of that technique, but I know in trig substitution at 8.4 there were several places where you end up with something like the secant or a cosecant or integral of tangent. Well, just go ahead and use the table on those. But there will be one or two specifically where I say use the table so you don't have to derive how we get the formula. But most of them will be show your work, show the technique that you're using. But within that, there may be a little bit you can use on the table. The next worksheet we did was 8.3, which deals with the trig identities. And the main ones there, we looked at sine squared x plus cosine squared x equals 1, being able to change, like if we have cosine to the 4th x, well, we can change that to 1 minus sine squared x and then quantity squared, cosine squared squared. But using that, or let's see, tangent, not tax, tangent x, tangent squared x plus 1 will equal secant squared x, or maybe it's tangent squared x equals secant squared x minus 1. You will be allowed a sheet of paper, so you might want to write those formulas down just to make sure, especially on this one, get the sign the correct way. I always have to double check, is it tangent squared plus 1 or is it minus 1? Get my units on here, 8.5 by 11 inches, both sides. Yes?
I have a question. Will you get to a point where it's going to...
Now main use of these trig identities, sometimes we have to use these, other times, like if we have something like that, well, what do we need to do?
The u equals sign.
Yeah, that's just a straightforward substitution. Du would be the cosine x dx, and that takes care of cosine. So we basically have the integral of u to the fourth du. Okay. Now, some of the combinations, probably the ones I put on the test, won't quite be that easy, but maybe it would be sine to the fourth cosine cubed x. Well, it'd still be, let u equal sine x. Du would still be the cosine x dx.
Wouldn't you just pull out like a cosine?
We basically have to change that and then use your 1 minus sine squared x to, so that's going to be the types of problems here, whether with the sines, cosines, or tangents and secants. But these identities will be able to turn it into one or the other. Yeah.
Will you do an example with just sine of 4x, sine.
Okay. So this is really kind of the easy stuff where you have the one cosine that you can pull out and then just deal with the sine. But yeah, if it's just, say, if we don't have a cosine part, then what do? Well, this would be where we have to use a different trig identity. Okay. And let's see. Yeah, with this sine, we're going to need to kind of think of it in two parts. But the sine squared x, we'd have one, is it minus? I think sine is the minus. Cosine of 2x all over 2. Now the other one that goes with this, cosine squared x, will be 1 plus cosine 2x over 2. So that's the difference in these. The only difference in these identities is the minus and the plus. So from there then, we still have quite a bit to do on this one, but at least we're not dealing with the fourth power. But we will need to multiply the binomials together and keep going. The denominators we can pull out in front. Let's see, we'd have 1 minus 2 cosine 2x, and then plus cosine squared 2x. Okay. And from here, hopefully you can do this one. And even, I mean, this one is straightforward. You'd have to do a little bit of substitution. Integrating cosine is sine. Make sure your u is correct and du. But here, this one we'd have to use this again. Okay. Now, cosine squared of 2x, not just cosine squared of x, this part would turn into what? 4x, because we're taking 2 times the inside. So 2 times 2x. And then all of that over 2. So I won't go any farther on this, but lots of little tiny details you got to keep track of, and we still have several integrations to do. Don't lose the constant out in front. Now that would be times everything. And then this one would be just times these two terms. So watch those constants. Lots and lots of steps on these. So, okay, does that answer your question good enough on that one? So that's kind of our sine and cosine, and then the tangent and secant works very similarly. The difference with tangents and secants is let u equal tangent x, du is going to be secant squared x. So we need more than just secant x out there. We need a secant squared for the du part. But then tangent, or the secant, let u equal secant x, du is both tangent x times secant x. So that gets a little trickier, making sure we choose the right u, but should be able to kind of fall into place on those. Okay, so that's the 8.3 with the trig identities and major substitution there. Next we went to the 8.5, which was the partial fractions. And with these, again, the process of changing something like this over that. Well, first thing we'd need to do is what? Okay, factor the denominator. And we'd end up with 3 linear factors. So we could change that into a over x plus b over x minus 2 plus c over x plus 2, or whatever order you put them in, doesn't really matter. And then that's going to equal this one. And when we multiply both sides by our x minus 2, and x plus 2, we get this left over. And then that's equal to x squared minus x plus 1. And he shows one way on the videos, and I showed you a little different direction you could go. Either way, you should get the same value. Sometimes it's easier one way, sometimes it's easier the other way. So I don't care which direction you go, I just want to see the right answer. Okay. Now, a couple more kind of different details from here. First of all, we kind of saw this a little bit in 8.1, but it shows up again with partial fractions. If the numerator has a higher exponent than the denominator, or if they're the same, what do we have to do? Okay, we have to do long division if numerator has a larger or equal to degree than the denominator. So you got to go through long division, and then probably one part of it you'll have to go through the partial fractions. Don't forget about that. And then the other kind of more complicated partial fractions, if we have a denominator, let's see. Just make it easy in the top. If we have this, well, again, we could factor out an x, but this time we're left with an irreducible quadratic factor. And the setup there, still have the a over x, but the x squared plus 4 would have what on top? Oops.
bx plus c.
Right. Our irreducible quadratic factor, we have the bx plus c in the top rather than just a b. And let's see, one other possibility, we'll just I'll go this way. How would we factor that one? And then the x squared is a repeated factor, so we have to treat that a little differently. We'd still have
Plus b over x squared.
right, a over x plus b over x squared. So any repeated factors, the denominator of the first one is to the first power, then to the second power, and then our lone x plus 4, we have that. So some different possibilities for the partial fractions, but then lots of little algebra stuff and careful with the signs and all that good stuff. And then integrating, well, most of these, like these parts would turn in, integral would end up being a natural log, but careful with this one, this can kind of throw us once in a while. Integrate x to the negative 2, okay, and then here, something like that, we may have to split that up. If we end up, let's say we get a b is 1 and c is, well, 1. Something like that, well, we'd have to separate it into x over x squared plus 4 plus 1 over x squared plus 4. And this one we'd have to do what to? Substitution. Let u equal x squared plus 4x, then the du would take care of that x in the numerator. Okay. And then, let's see, we'd have a 2x dx for du, so 1/2, don't lose the 1/2 in there. So
that's what you will have to do for that one.
yep, for just this one part. And then what about this one?
Partial fraction.
Not with the x squared plus 4.
It's just natural log, right?
Not natural log. It's one of our formulas.
Arctangent?
Yeah, arctangent. Arctangent. And in that case, you can just use the table of formulas for that. With this not being 1, you got your a. Formula says u squared plus a squared in the denominator, so a would be 2 in this case. Make sure you get those in the right places. So. Okay, questions there? Now, integration by parts, this is where we have like a product of something. Some of them are fairly straightforward, but others get kind of tricky. And let's go ahead. On the worksheet, it talks about the tabular method, the table, making a table. And I thought on the videos he had mentioned something like that, but he doesn't. It's involving a repeated integration by parts. And we'll take a look at one of those.
It's x cubed sine of x.
Okay. And this was, well, was it 25 on the worksheet? and then also number, was it 51? Now on 25, you just were to do it the regular way, and it repeated, and you did the next part, integration by parts and so forth. But same problem on 51, they say use the tabular method. And it's going to be the same process, but it organizes your repeated integration by parts, makes it a little bit easier, or, well, a little bit quicker. Maybe not so much easier, but quicker anyway in setting it up. So what we have to do, we'll have 3 parts to the table. The sign, we'll talk about that here in a second. Then we'll have our U and we'll have our dV. Now, the first integration by parts will end up with a positive, and we'll see where the other signs come in. But in this case, our U we would want as x cubed. And then dV, we could do the sine x. Now, this is setting up a little bit differently than how he did it on the videos. I think he was putting the dV down here and then doing the V up here. But the idea of what we do with the U and the V will be the same, just set up a little differently. So in this case, V would turn out to be what? Okay. And then du, and get 3x squared. Well, in our normal process, we would take u times v and then minus the integral of v du. And then we would go again, we'd actually have 2 or 3 more integration by parts here. So it gets long and drawn out doing it this way. You can do it this way, but the tabular method makes this go a little quicker. And we'll see signs, we'll see what happens there. Now the sign, notice the first part starts out with the positive. It will turn into a negative because v is negative, but that's just coincidence. The first row of our antiderivative will be the sine and u, and then dropping down to v. Notice that's what we have right here. Okay. Then, because of the minus on the integral of v du, the next row will involve a negative sign. Okay. And then, well, from this, if we were doing it the long way, we'd have this to work with. We'd let this be u and this be dv and go from there. Well, we already have that kind of set up in our table. So du be 6x, v will be negative sine x, and then our next term, had we done this the long way, our next term would be this. So we'd have minus 3x squared times negative sine x. We have that as our first term, this is our next term, and then go again. Okay. We've got 6x as u, so du will be 6. Negative sine x as dv, so v will be cosine x. And then this will actually be the next one. And then one more, we'll have minus, this will be the,
0.
okay, yeah. Integrate, or not integrate, derivative would be 0, and then v, okay, integral of cosine is sine. And so we'd have that as our next line. And then we can stop because technically our next line would involve 0 times whatever this is. Well, that shows us where we stop on the tabular method. So x cubed sine x, we would have this, and this, and this, and this, and then plus c. So, yep.
So how are you getting the sign? Is it alternating?
This right here, that's because of the way integration by parts works.
Oh, so it's the, okay.
So we have this first column with the sign to take care of this right here. So we don't have to worry about that part of it as we're listing.
How will you rewrite the whole thing then?
Okay, so rewriting the whole thing, kind of ran out of room, but we'll stick it right up here. We'd have x cubed times negative cosine x, okay, which was our first row, our first operation. Then minus 3x squared times negative sine x. Now again, this sine is not necessarily what we'll end up with for our final answer. That's just part of the process. This negative would actually be times this negative, so our second term would be plus, but using the tabular method, we get the negative of that times that. And then plus 6x cosine x, then minus 6 sine x plus the c. And of course, we would usually put the negative out in front. We'd go ahead and combine those and make that a plus. But that's where this sign, this is very important in using the tabular method. But it saves a lot of steps. It organizes it nicely to make sure we get the right signs and so forth. So if you want to try that, some of these can get fairly lengthy with integration by parts. Okay, questions? Now the trig substitution, this is where start out with something in terms of x, doesn't look like a trig function at all, but because of the combinations of x, or x squared really, we can let x equal 2 sine theta, or let x equal 5 tangent theta, and then plug that in. Using the trig identities, we can simplify our integral down. So what you probably will want to do, save a little time on the test, is make sure you have the correct form. Let's say we have something like this. Well, something like that, we could use a straight substitution. But let's say we have x cubed on top. That one you couldn't do straight substitution, but something like that. This, we would want to let x equal what?
5 sine of x? Oh, sine of theta.
Okay, right, 5 sine of theta. Because when we substitute that in here, squaring the 5, we get 25 times sine squared, and then factoring out the 25, well, square root of 25 is 5. 1 minus sine squared theta is cosine squared theta. Square root of cosine squared theta would be cosine theta. So that right there, I mean, if you want to put that on your note card as well, if you choose x to be 5 sine theta, then this part right here, you can go ahead and substitute directly into that. And the other substitution we need is your dx would be 5 cosine theta as well. Substitute all that in. The square root was 5 cosine theta, and dx was 5 cosine theta. It's technically d theta, get that on there. And we've changed this integral into, well, 5 divided by 5, cosine divided by cosine. We've got 5 cubed, or 125, times sine cubed theta. Now, we still have a lot to do on this, but at least it's in a doable form. And then what would we need to do with this part to integrate it? Okay. That's where got to go back to 8.3, that idea. Sine squared times sine theta.
So then you will substitute the sine squared.
Change that into
1 minus
1 minus
cosine.
cosine squared theta, and substitution and so forth. Now, that will get you an integral and antiderivative answer, but in terms of, say, sine theta or cosine squared theta, cosine cubed theta, something like that. But then we got to go back and resubstitute, use your trig triangle and figure out sine theta would be x over 5, but cosine theta would be something a little, well, cosine theta would be that square root over 5. So these get really, really long and drawn out. Just lots and lots of little steps. Be careful. Take your time on those. But definitely the main thing is recognizing what the initial substitution would be. And again, I would suggest writing out there's 3 different possible substitutions. Make sure you have all 3 of those written out. I know you probably remember some of them, but just to be on the safe side, write all 3 of them out. This one, if it's a minus x squared, and that's where you use x equals a sine theta, using a in general based on what we have here. X squared minus a squared, well, there you would use what? Secant theta. And then x squared plus something, you would use your tangent. Okay? Any questions on those? Any particular problems that you want to see on the trig sub? So, 10 problems. If you want, you can come in early and get started early, or you can stay late. Hopefully you'll be able to get it done tomorrow.